Okay, so thank you very much for having me. So instead, very timely, this whole workshop and hopefully the talk as well. The talk is going to be about computational scientific discovery, which it means to me how a physicist or how a bunch of physicists try to teach computers to find mathematical models from data. Okay, so this is what the talk is going to be about. And let me put this down so I can see all of you. And I want to motivate this with two problems, okay? So one from physics and one not necessarily from physics, although physicists have been interested in this problem, okay? So again, I'm going to introduce these two problems. I'm going to motivate the problem, what we want, the algorithms or the set of tools that we want to propose. And then I'm going to show you how we do it, okay? Okay, so the first problem that I want to talk about is related to turbulence, okay? So this guy here is Johann Nikuradze, and in 1933, so almost 90 years ago now, he performed some experiments on the friction that fluids feel when they go through a rough pipe, okay? So what he did is he assembled this device here. There is a pipe here, and inside this pipe, on the walls of this pipe, there are he put grains of sand to make, like of different sizes, to make the pipe more or less rough, okay? So then he pumped some water or some fluids through this pipe at different velocities, and he measured the pressure drop basically from here to here, which is, well, the loss that you have because of turbulence, right? The dissipation of energy because of turbulence in this device, right? This is an important problem for engineers because, of course, pressure drops means that you have to push liquids through pipes for them to move, and that means money, right? So it's an important problem, right? So he came up with this data, which is called the Nikuradze data set. It's relatively old. And what he plots here is the friction factor, and here the velocity of the fluid, okay, the Reynolds number, the velocity of the fluid. And he does that, or he did that for different levels of roughness in the pipe, right? When you have low roughness, you have low friction. And then as you increase the roughness of the pipe, you have more and more friction, okay? And the shape of these curves is somewhat particular. So at small Reynolds, when the velocity of the fluid is small, the friction does not depend on the roughness of the pipe. And this regime is relatively well understood. But then after some point, then the roughness starts playing a role, and you get these funky curves here that depend on the roughness, okay? Basically, if you look at how people have tried to model, you know that, well, for those of you that are physicists or engineers probably know that turbulence is one of the notoriously difficult problems to solve in physics, right? So it's been 90 years, but people still publish papers trying to give models for this data, like physical, like mechanistic models of this data. And there's still discussion about which models are better or worse. No one knows the exact expression for this. And again, there is discrepancies on why people think, what people think is the correct way of modeling this data. Okay, so it's kind of surprising that perhaps that after 90 years, we haven't been able to find analytical curves, like closed form expressions for these curves, okay? It seems they seem smooth enough and so on, so it seems that we should be able to find closed form expressions for them. Okay, so this is the first problem, the Nikuradze data set related to turbulence, okay? Now, the second problem I want to talk about, again, it's totally unrelated, and it's related to mobility of people, right? And the question we want to ask in this question is whether we can model or find models that predict how many people are going to travel from one city to another, okay? So this thing here is a map of Texas in the US. You have cities in there and flows of people between them. So here, orange is a lot of people commuting between persons of cities. This is big cities, there are large flows, and then between small cities, there are smaller flows and so on. And basically, we have lots of information about each one of the cities. We know their populations. We know whether they have restaurants in them or whether they have schools and so on. And we know the distance between cities, and we would like to find models that predict how many people on a given week, let's say, are going to go from one origin city to a destination city, are going to commute from one origin to one destination. Okay, so for many, many years, this has been modeled using what is called gravity models, which basically assume that the number of people that go from one origin to one destination city can be modeled as a gravitational-like law, right? So basically, as the product of the populations of the origin and destination divided by some monotonically increasing function of the distance, okay? So basically, the number of people that move between two cities grows with the population of the cities and decreases with distance. That's basically what gravity models are. And these models have been used, again, for like 70 years or something like this, since the 50s, 1950s, okay? And of course, these models are very easy to interpret, right? And they make predictions that are not totally crazy, but they are not accurate, right? They are qualitatively correct, but they are not great predictions. Okay, so this is one end of the modeling spectrum for this problem of modeling mobility flows between cities. Now, much more recently, people have started proposing models that are based on deep learning, okay? So we go from a model that has one parameter and 3 features, right? To models that take into account, again, number of restaurants, number of schools, number of roads, all sorts of things, right? So in this particular model, it's called a deep gravity model. They use 19 features for each city, right? 19 characteristics for each city, for the origin, and 19 for the destination, plus the distance. And then they train a very complicated model with, I don't know, hundreds of thousands of parameters hidden in them. And they end up making predictions that are more accurate than the gravity models, right? So basically, in the modeling spectrum, we have 2 ends, right? One, very simple, interpretable models that don't make very good predictions. And then the other, very big models that are very hard to interpret and that make more accurate predictions, right? And again, what we would like to do is to find closed form expressions, perhaps models that look more like this, but are able to make predictions more like this, okay? So what these are the 2 problems I wanted to introduce. One, turbulence and friction, and the other one, mobility between cities. And what they have in common from our point of view is that in both cases, we want to find expressions like this, right? We want to predict the friction as a function of the roughness and the turbulence and the velocity of the fluid in one case. And we want to predict the number of people that are going to travel from one city to another as a function of whatever, populations, distance, and what have you. So what we want to do is design a machine scientist that automates the task of building this model, right? Of y equals a given function of these features, okay? So of course, this applies to any machine learning approach, right? Or any statistical modeling approach, if you want. We always want to relate some target variable, some output to some inputs, to some features. What's different in our approach is that we want to do this with closed form mathematical models, okay? So what we want to do is to find simple mathematical models that look something like this: f of x equals a plus a1x, or f of x equals logarithm of the sine of the exponential of x to the minus 8, things like this that help us to model these 2 systems that I've introduced, okay? And this thing we call a machine scientist. It's been called many things during many years, as people here know very well. It goes under, solving this problem goes under the name of symbolic regression, equation discovery, systems identification in engineering, and many other names, perhaps. But the problem, again, is finding closed form expressions that relate inputs to outputs, okay? With simple expressions like this, right? I will not give you a very precise definition of what a closed form model is, but in reality, what we are going to do is to use elementary functions like trigonometric functions, hyperbolic functions, perhaps exponentials, logarithms, and things like this to try to model our system. Okay, so in summary, some people at Quantum Magazine did this very nice drawing of our work. So basically what we want to do is to take data, noisy data, real data from physical systems, from social systems, what have you, biological systems, and then put this to our machine scientists and get closed form expressions out of there. Okay, so now as I said at the beginning, I'm a physicist. My collaborators are physicists as well. So even knowing that there are algorithms, many algorithms that do these sort of things, our starting point is a bit different, okay? And our starting point is to put very strong conditions about what we want this machine or machine scientists to do. Okay, so we formalize this into what we call a desiderata, right? Like a bunch of things that we impose on our algorithms to have. Okay, these are conditions that we want our machine scientists to fulfill. Okay, so the first one is just the definition of the problem. Machine scientists has to take data as input and produce closed form, interpretable mathematical models of the data. So this is what I've just stated. The next two are a bit more substantial than this. So basically, the first one is that it should be able to quantitatively and rigorously from first principles meaning from first mathematical principles on strong mathematical grounds, it should be able to establish the plausibility of models, okay? So typically, when people do symbolic regression, equation discovery, they start by fixing some quality function, right? We want to minimize the prediction error, or we want to minimize the error on the training data, or whatever, right? So typically, what error you put in there is arbitrary, right? I can minimize mean squared error, or I can minimize mean absolute error. I have many possibilities in there. So the first condition that we imposed on our machine scientists is that it has to derive this quality function, if you want to call it like that, from on some solid mathematical grounds. Okay, we are not free to choose what we are going to optimize. We want to derive what we are going to optimize. Okay, so this is the first one, rigorous and quantitative plausibilities for each model. And the second one is, okay, we are looking for mathematical expressions, right? We have some data, we have many mathematical expressions that could describe the data, and we want to keep searching this space of mathematical expressions until we find something that fits the data well, okay? So again, standard approaches to symbolic regression or equation discovery propose heuristics here, right? They say, well, we are going to do this sort of search in the space of possible models, or we are going to use a genetic algorithm to look for models or things like this. So we want, rather than proposing a heuristic here as well, what we want to do is to propose something that is well grounded on mathematics, and in particular, as you will see, in probability theory. Okay, so these are the things that we, or the conditions that we impose on our machine scientists. And although I don't have time to go into the details of each particular symbolic regression equation discovery approach, I claim that these are not very common, to say the least, properties in symbolic regression, okay? Conditions in symbolic regression. Okay, so again, we are statistical physicists, and we believe that there are theorems that prove that when you are dealing with uncertainty, right, when you have noisy data, for instance, and you are searching from a large space of mathematical models that could describe the data, one has to use, when there is uncertainty about something in the world, we have to use probability theory, right? There is something called the Cox theorem that tells us that there is only one way to deal properly with uncertainty, which is using the rules of probability theory. And that means the rules that we learn in high school, right? The sum rule and the product rule of probability theory. So here because since we have uncertainty, right, again, we want to find models like this. The output is a function of a given unknown function of the inputs, right? What we claim is that the whole problem is described by this probability distribution that gives us the probability of the function of expression, if you want, f, function f, being the correct one that generated the data, given the data, right? So we claim that this is the distribution that we want to find. If we are able to calculate the probability of the given function f, given the data, the probability of f being the correct function, the correct model, given the data, if we are able to calculate this, then we've quantified the plausibility of the models, and we've solved at least the first condition in the desiderata, okay? So this is called the posterior of our expressions, right? Is the probability of our models given the data. And again, we claim that this posterior, this probability distribution, encapsulates the full probabilistic solution of the problem, okay, of symbolic regression. If we are able to assign a probability, a plausibility to each model, then we are in good shape to compare models to each other, basically, okay? Okay, so how do we calculate this plausibility over models. This is the mathematical part of the talk. I hope that everyone will be able to follow, but at the end, there will be a summary. Okay, so we use probability theory, which some people like to call Bayesian model selection, but it's just probability. It sounds scary, and it sounds like a sect, right? There is the Bayesians that do Bayesian things, and the frequentists that do frequentist things. I don't like those. We use probability theory, okay? We use the theory of probability, which we have theorems that tell us that is the proper way to deal with uncertainty, okay? So when we want to use models, probability theory, sorry, to select models, we use this equation here, which is one particular incarnation of Bayes' theorem, okay? What we say is that the probability of a model M being the correct one given the data, right? This is the posterior we want to find, the probability of a model given the data. We can always write as a function of the probability of the data given the model times a prior expectation about models, okay? So this is the typical Bayesian update rule, right? We say, we start from some expectations about which models are more plausible than others, and then we update those expectations based on the ability of the models to describe the data. Okay? Okay, now when we have models, this is in general when we have models, general models, right? When we have, in our case, remember we have models F with parameters theta, so we have to modify this expression a little bit, right? So instead of the probability of a model given the data, what we have is probability of our expression, our model, and the parameters of that expression given the data. And it's just exactly the same expression as before, except that every time I had model before, now I have my expression and my parameters. And I do exactly the same as before. This is exactly the same, just replacing model by expression plus parameters. And now the only difference is because I'm not interested in the parameters, I have to marginalize, I have to integrate over all parameter values. And the expression that I had before, which was probability of the model equals the likelihood times the prior, right? The names that we typically give these things. Now we have the probability of the model is the prior of the over models, the probability that I assign to models a priori, times some integrated likelihood. So it's the same function as this, but now I have to integrate it over parameters, okay? So this is how I quantify the goodness of a model, basically. To quantify the goodness of a model, I have to calculate this integral here, okay? So again, this is not complicated, right? If I have a model, let's say a linear model about my data, I know what's the probability of generating some data from my model, right? It's a Gaussian, right, around the linear model and so on, like we do in ordinary regression. All I have to do is integrate these over parameter values, and that tells me how plausible my model is, my linear model is, okay? Very good. So the question is, this is the exact calculation. Basically, if you and I are looking for models and we disagree on this, then, I mean, someone is doing something very wrong, right? This is what probability theory tells us we have to do when we want to find models from data. If I have another method that does not agree with this, so it quantifies the quality of models with some quantity, perhaps mean squared error or whatever, that does not agree with this, then that model is doing something wrong, okay? Because this is probability theory. We know from Cox theorems that this is the proper way to select models, okay? Now, the question is not whether this is the correct way of doing it or not. The question is that it is useful or not. We can use it for something or not. And the answer is that with some approximations, we can, okay? So again, this is just what I've written in the previous slide. The probability of the model given the data, of a given expression given the data, is this integral here. And this is just a definition. We can call this e to the minus L, or if you're a physicist, you can call it e to the minus h if you want, divided by P of D. And again, this is just a definition of what L is. And it turns out that with some approximations, some standard approximations, we can calculate what this L is, okay? So this L is called, if you come from information theory, you'll call this L description length. It's the number of bits that you need to send me your model and your the data, the model and the data. If you're a physicist, you can call it energy if you want. And if you are a probability theory person, you can just call it the logarithm of the probability or minus the logarithm of the probability. But whatever you call it, the thing is that this integral can, for the regression problems, for the problem that we are interested in finding models from data, you can approximate it in this way, okay? So basically, you can do approximations to this integral the Laplace approximation in particular. And what you get is that this description length, this energy, is the Bayesian something that is called the Bayesian information criterion, which is something I can calculate from the data. If you know what it is, good. If you don't, it's okay. Just the only thing that matters is that you can calculate it from the data. And then some prior expectations about your model. Okay, so we have some quality function here that has some part that describes how well the model fits the data, which is given by this B, this Bayesian information criterion. This is a goodness of fit measure. And this is a measure of our prior expectations about the model. Okay. So now we know how to quantify, right? We know what we have to minimize in order to have the best possible model. Look at this. What we want to do is select a model that it's the most plausible among all possible models, right? We want to maximize this posterior. We want to find the F that maximizes this posterior. Maximizing this P is equivalent to minimizing the description length, right? So it means that the model we are looking for is the one that has the minimum L, the minimum energy, the minimum description length, whatever you want to call it. But now we have a quality measure for models that is derived from probabilistic considerations, right? It's not heuristic. It's something that is derived from probabilistic considerations. Okay, so why do we like this probabilistic approach? I think I will skip through this in order to be able to finish on time. But basically, there are, again, well, one of the arguments that I already mentioned, right? So there is Cox theorem. Cox theorem tells you that if you want to deal with uncertainty, you have to use probability theory. If you don't use probability theory, you are violating some very basic considerations about the world. Like you are violating some common sense considerations. Since here we follow the rules of probability, again, this is except for the approximation at the end, basically, you have to agree with this formulation, right? This is the thing that you should minimize in order to get the correct model without violating some very basic considerations of common sense and so on. There are other arguments, right? Information theory, right? We've talked that what we are doing is minimizing the description length. Minimizing the description length means that the model we are going to select by minimizing this quantity is the model that compresses the data the best. If I want to send you my model or the model and the data, I cannot do better in terms of zipping the file, if you want, than selecting this criterion here, right? And perhaps the argument that is the most convincing is the Dutch book argument. Imagine that two people are going to like they are given some data that is generated from one of these Fs. We don't know which one. And one is going to use probability theory to select the most plausible model. And someone else is going to select something else, right? Let's say minimizing the squared error in the validation set or whatever. Well, there are two options here. Either they agree on the solution or the person that does not use probability theory is going to lose money for sure, right? If two people are going to bet money on which one is the correct model, the one that uses probability theory is guaranteed to win money, okay? This is the Dutch book argument of probability theory. Okay, so with this, we've solved the first problem, okay? Remember the conditions we've imposed. We want closed form expressions, and we want to be able to quantify the goodness of models, the plausibility of models. We've done it with this description length, with this probabilistic approach. Now, the second challenge is how do we explore the space of models, right? We have infinitely many mathematical expressions. How do we guide our search toward models that are meaningful for a given data set? Okay, so with this, we do something similar to what people in symbolic regression is, which is represent expressions as trees, okay? So this thing here, for instance, represents C1 times X, right? And now I can make changes to these expressions to get different expressions, right? So for instance, I can add here a root to this tree, and now this expression C1 times X becomes C1 times X plus C2, okay? So this is one of the type of movements that we can do, one of the types of moves that we can do. We can do other types of moves. So for instance, we can replace all of this branch here with something like X, or we can replace the plus operation here by a divided by operation here and so on. So we can do all of these things. And there are two key ideas here. One is that we can represent expressions like these trees, right? And the other one is that we can change from one expression to another by designing some, let's say, reasonable set of moves like these ones that I've proposed here, right? Then as long as I can, with these moves, I can generate all possible expressions, I'm guaranteed to at least be able, at least asymptotically in the edge of the universe, to explore all possible mathematical expressions. Okay? Now, okay, this gives us a way of moving from one expression to another, but we still don't know how to, whether when we try to move from this expression to this other expression, whether we are going to accept or not. In other words, we know how to walk this space of mathematical expressions, but we still don't know how to guide the search towards models that are appropriate for the data, okay? But in reality, this is not different from a physics problem, right? What we have is that each expression has an energy associated to it. That is the description length, right? If you give me an expression, I can and some data, I can calculate the energy, the description length of that model. And then I can try a different model and apply the Metropolis algorithm, which is what physicists, for instance, use, also computer scientists, when they want to explore an energy landscape like this, right? So typically what you have in physics is that you have different configurations of your system, and then you want to calculate thermodynamic properties, let's say, and what you do is you change your configuration a little bit and accept or reject depending on what happens to the energy. So what we do here is exactly the same. You give me some data, you give me some model, I change the model a little bit, look if the description length decreases or not, and if it decreases, I accept, and if it doesn't decrease, I apply the Metropolis algorithm to decide whether to accept or not. But the summary is that we can explore this in a way that guarantees that we are going to give more importance to the models that are more relevant, okay? Okay, so if you got lost, this is a good point to come back to the talk. So basically, we've designed the machine scientist, okay? So on the one hand, we have a way of quantifying the quality of models. You give me some data, you give me some model, I can calculate the description length that tells me how plausible that model is. And on the other way, we have a way of exploring the space of possible models by using Metropolis Hastings, okay? The algorithm that physicists use for exploring energy landscapes, okay? Okay, so let's skip this. The question is, does it work? Can you push? Thank you. You came right at the right time for this. Okay, so can you stop it for a second? And okay, so well, can you put it at the beginning? Almost? Okay, what you have here is the following. You have some data, some function y that depends on x1 and x2. Okay, and in this case, the correct function, it doesn't matter. It's a combination of trigonometric functions and quadratic functions. Okay, so we have f as a function of x1 and x2. And then we are given the points in here. You hear me, right? Okay, sorry. Okay, so you see points here that this is what we are given. We are given these points, and what we have to do is to find the function that generated those points. Those points are noisy and so on. They have noise in the x-axis. And what the machine scientist has to do is to find the correct surface for this. So the blue surface is what the machine scientist is proposing at this point, and the points are the data, okay? And what you have here in this plot here on the upper right corner is the description length as a function of the iteration of the search process, okay? The Markov chain step. So you see that you look only at the blue line. The others, I don't have time to explain, and it corresponds to this graph, but I don't have time to explain. But you have to look at the blue line here. That's the description length. So what we want is this curve to go down. We are finding models with shorter and shorter description lengths. The shorter and shorter energies, better, or smaller and smaller energies, better models. And eventually they should reach the correct model and oscillate around that. So now can you switch it on again? Okay, and you can ignore all the other plots. So you see the machine scientist is trying different expressions here. You cannot see them, but they are up there until they find, like, this is the correct expression. And now it changes a little bit, it oscillates, but mostly stays within the correct expression and stays there, okay? So given data, by running this machine scientist, basically we can do this, right? Even if the data is noisy, we propose models, and eventually, at least asymptotically, we are guaranteed to sample models that describe the data well, that are the most plausible models. Okay, so it works if you give it some data for which you know that generating, like the function that generated it, it recovers the correct function. We have a bunch of examples of this. Whoops. Okay, so now let's see if it works in the wild, right, with real data. So this is, now I'm going to solve the first like the two motivating examples, or not solve, but I'm going to see how the machine scientist does in the two examples that I discussed at the beginning, right? So remember, this one is about friction as a function of velocity of a fluid and the roughness of the pipe in which it's moving. Okay, so the first thing we can do is to take the data and give it to the machine scientist and ask which are the models that describe this data, okay? So in this case, the gray points are the data that we use, that we feed the machine scientist, that we use for training, if you want to use that language. We give the machine scientist, and the machine scientist starts exploring expressions. And eventually, it finds expressions like these ones here, like the red lines here. Keep in mind that this is one expression for all the curves here. So all the curves is not one curve for each line. It's the same function for the same functional form for each line. And well, it fits the data pretty well, right? I think we will all agree. But it gives very different expressions, right? There are many expressions that describe this data well. So well, in terms of modeling this, I think we are successful. We can find good models for this. In terms of getting understanding, I'm not so sure, right? I think, well, I'm not sure this is very insightful. It's certainly more insightful than a neural network, I would say, with 10 to the 10 parameters. These things have like 8 parameters or 7 or something like this, but it's still not very insightful. And okay, there is this thing that John von Neumann said, right? I think he said, well, if you give me 3 parameters, I can fit an elephant, and with 4, I can make it wag the tail, right? So this has more than 4, so I guess we could make it move. So the question is are we learning something from this? And I think the answer is yes, and I'm going to try to argue that. The first one is whether we can use this to make predictions outside the training region. Okay, so in this case here, what you have is we train the machine scientist with the gray points, and we ask it to make some predictions outside of the training range. Okay, so in this case, we are training with low levels of roughness, and we are asking for a prediction for the black points up there, which correspond to high values of the roughness. Okay, the red line is the machine scientist, and the other lines are different machine learning algorithms, including some symbolic regression and Gaussian processes, standard, let's say, algorithms, statistical learning algorithms. And what you have here is the error in the predictions, and the red always does better than the others, right? So it makes much better predictions than the others. It's still not capturing the physics, right, of the constant value here, but it's making reasonable predictions. So this is not fitting an elephant. This is something different, right? It's a bit different. And here we are doing the same, but with intermediate values and high values of the velocity, and it still makes good predictions in here, right? So again, this is a bit better than fitting an elephant. It's making predictions about the ear of the elephant, which you haven't seen perhaps, or something like this, right? Okay, but perhaps better, we can use this to actually learn some physics, I think. I'm going to argue this in 2 minutes. So the way people have been addressing this problem with this data is the following. We know that these data have these complicated shapes. We don't know how to explain these shapes, but what we can do is propose scaling functions for this. This is something that we physicists do. Propose ways of transforming the data, combinations of the data, in such a way that all the curves fall into a single line. Okay? Now, there are different proposals that people have been making, from very recent in 2006 to very old. For instance, this is the scaling that the same Prandtl, well, Prandtl was Nicoraz's advisor, so this was done in the 1930s of the previous century. So we have from very old scalings to new theories that have been proposed about how these things can be scaled. So what we can do, so these curves are scaled, we can apply the machine scientist to these curves here. So not to the unscaled data, but to the scaled data. Now we have a single function that only depends on one variable. You see them as the orange line here, the green line, the red line, and so on. And then since we have an analytical expression for this curve, we can do an unscale the data. Okay, so this is what we do here. We take the scaling, we feed the scaling, and then unscale the data and the function. And we see that sometimes that works terribly, and sometimes it works very well. So this gives a way, for instance, to quantify how good a scaling is for this data, right? And surprisingly enough, in this case, we proved that we showed that the best scaling is the one that was proposed 90 years ago, right? People have been proposing scalings for 90 years. The best one was the original one, okay? It's the one that makes the least error when you do this process of unscaling. Okay, and another thing that we can do is look at the form or the functional form of this curve for the scale data. And you see that now this functional form is a combination basically of two exponentials of the scale variable. So, well, I'm not an expert in fluid mechanics, but I suspect that there can be theories that explain why we have two exponentials. That's something that we can probably interpret and get insight from, okay? Okay, so let's go to the second example very quickly. So remember, the second example was about modeling modeling mobility between cities in the world. We have very simple models that are not very predictive, and we have very complicated models that are predictive, but not interpretable. And what we want to do is to see if the machine scientists can find models that are almost as simple as this, or this sort of models, and predict as well as this. Okay, so we take data on mobility between cities, we feed it to the machine scientist, and we get expressions. And the expressions that we get are things like this, okay, like this expression here and this expression here. Okay, so these models are definitely more complicated than the gravity model. Remember, the gravity model is just product of the populations divided by some distance. But what we have here, it's what we call gravity-like, right? So what we have here is a model that only depends on the population at the origin, shifted by some quantity, multiplied by the population at the destination, shifted by some quantity, and then basically a power of that divided by distance again, right? So this is not a gravity model, but it's a gravity-like model. It's a model that is mathematically pretty simple and pretty similar to the gravity model that has been used. Now the question, okay, these models are not as simple as this. The question is, are they predictive or not of mobility flows? And very quickly, basically the answer is yes. Okay, so what you have here is different performance metrics, right? Different ways of measuring how well an algorithm does. What you have here is the performance ratio, which is basically the higher the better in that metric. And what you have here in different colors are different types of models, okay? So bear with me. The greenish models are gravity models, like these very simple models. They typically do worse than the others. The blue and purple and pinkish are, well, the blue, let's say, are standard statistical learning algorithms, random forests or things like this. And pink is the gravity model. And the orange-brown ones are the models that the machine scientist finds. And what you can see is that performance-wise, these expressions that we found that are very simple or relatively simple, typically do better than deep gravity, the deep learning. And they do the same as in as a random forest. And well, it's important to keep in mind that the machine scientist only uses population and distance. Random forest is using 39 things, right? What I mentioned before: number of schools, number of restaurants, number of roads, and so on. And even perhaps more strikingly, so again, with very simple models, we can predict mobility flows better than deep gravity, and as well as much more complicated models in terms of features. This is for 6 states. Then the reviewer number 2 asked us to do, okay, with the same models, you do 6 more states to prove me that this is not a fluke and you are not overfitting. So we did this thing with 6 different states, with 6 new states, with the same models that we have learned for the 6 original states. And what we find is that the machine scientist not only predicts better or the same as random forest or more complicated models, it actually extrapolates much better, right? So the performance of the orange ones is better than all the others. Okay, so just to finish, up to here, everything has been pretty optimistic, right? You give me some data or you give us some data, and we are able to find closed form mathematical models that, I'm finishing. So you give me closed form mathematical models that approximate the data pretty well, right? But intuitively, there is something that sounds weird in there, right? So think with me. So imagine that you give me some data like this, right? The points here, and the true model is the surface in here, right? Now, it seems pretty intuitive that if you reduce the noise in this data infinitely, or if you give me enough data, infinite amount of data, I should eventually be able to identify the correct model, right? I mean, it might take me a long time, but if I find the correct model, I will know that this model is the correct one, right? So the model will be identifiable, okay? Now, on the other hand, if you start increasing the noise in this data, and now your function is like this, it's a smooth function between, let's say, -1 and 1, and your noise goes between 10 to the -10 and 10, or your noise is at the level of 10 to the 10, So your model is between -1 and 1, and your data and your noise. Okay, let me say it again. Your data, your model, the function goes between 0 and 1, let's say, and noise goes between 0 and 10 to the 10, you will not be able to identify the correct model. So at some point, it seems intuitive that at some point we should be able to detect the model, and we know that the probabilistic approach guarantees that you will. But if you keep increasing noise, at some point you will not be able to identify the model. Now, because our approach to identifying models is Bayes optimal, right? We can look at the limit when that happens. When do we lose the ability to find models? And we can find precise bounds to when we will stop being able to find models, right? And this is what we find, basically. So there is for some model M1, what we plot here is the noise level in the x-axis. So here you have very little noise, and on the right you have very high noise. And here you have the ability to identify the correct model by the machine scientist, but it's a general result. It's not limited to algorithms here will, in principle, be able to learn the correct model. Here, no algorithm whatsoever will be able to find the correct model, okay? Because of the noise. We proved this in a paper last year. Okay, so what you find is that this transition is abrupt. It's like a phase transition in physics, basically. So at some values of noise, you are able to detect the model very easily, but then suddenly you go to a level of noise in which you are never able to detect the correct model, okay? And this happens for different number of points, for different models, and we have arguments, like physical arguments, to actually know where this is going to happen, and to analytically find an expression where this is going to happen. So this is what you have here. This is the same curve that you've seen in the previous plot, right here, but just with the level of noise that it's scaled, okay? So we have analytical expressions for when you stop being able to detect the model, and when you scale the noise by that critical level of noise, what you find is that all the curves follow a similar pattern. So you go from this regime of not being able to learn, from being able to learn the model to never being able to learn the model, and this happens through this phase transition-like behavior. Okay, so this is all I wanted to say. I think I'm on time. So basically, we have the Bayesian machine scientist. I think it's a principal way of identifying closed-form models based from data. It works well. It finds good models in data. Closed-form models often are better than deep learning models. I've showed one example here with mobility. Of course, you cannot use this for things that have 10 to the 6 inputs, like images or things like this. But for scientific problems, you typically have models that depend on not so many things. And I think we should try and apply these sort of tools more often. And then this is the good news of the talk. The bad news is that depending on how noisy your data are, you at some point lose the ability to detect the model. And again, thanks to the rigorous probabilistic treatment of the problem, we can estimate when that is going to happen. Okay, so this is all I wanted to say. Thank you, my collaborators on all of these projects. Here you have QR codes for some of the papers that are involved on this. And thank you very much for being here at 9 and listening to me. Thank you.
Wait for people on Zoom. Just a second. Sorry for being late with the mic. I forgot.
Thank you, Roger. Fantastic talk. For the example that you were using, this is actually a number of curves, not just one.
A number of?
Of curves. It's not just one. So did you actually require the discovery process to find the same form but different parameters for each of those?
That one is a function. It's one surface, if you want. We plot it as different curves, but it's one surface. So the friction depends on the velocity of the fluid and the roughness. So we fit with one curve and one set of parameters in this case. So the machine scientist can do what you say, one curve. And actually, we do this for the other example. For the mobility, we use one model for all the states, but we allow different parameters for each state. I don't know if that was the one.
Yeah.
You were asking for the mobility or for the?
Yeah, no, I was actually asking first for the Reynolds thing,
Okay.
but I think this is common across many problems, that you require the same functional form, but for different cases have different values of the parameters.
Yes. So for the roughness example, we don't do that. It's just one function with one set of parameters. For the mobility, we do. So one expression, different values of different parameter values for each state. And that's something that, again, in the probabilistic setting, it's very easy. When you have different data sets, the description length is the sum of the description lengths of the sum of the bigs of the Bayesian information criterions, but with a single prior, because you are only proposing one expression. So again, everything is very natural, and you don't have any problems on fitting several data sets with different parameter values on the same functional form.
Okay. Thanks for the talk. It's very interesting topic and a little bit overlooked in comparison with machine learning. So I have two questions. The first one is whether this machine scientist approach allows us to get some kind of feature importance ranking, like which factors are most important in the equations that shows a better result.
Okay, let me answer one by one because I tend to forget questions. So yes, the answer is, again, because the probabilistic formalism is precise and it's well-grounded in mathematics, there is one, like in random forest, let's say, there are several approaches to calculate feature importance, right? You can randomize one feature and see how things change or get rid of the feature or whatever. But here is very precise. When we do the Markov chain Monte Carlo, I've been showing a few models that you get in each Monte Carlo run, but in reality, you get an ensemble of models, of equilibrium models, right? Models that are similarly plausible given the data. So if you want to establish the probability that a given feature actually appears in the model, what you have to do is to measure the frequency of that variable appearing in the ensemble. And that's the correct estimation of the probability of that feature being part of the model. So the answer is yes, we can establish very precisely the probability of each feature being part of the model or not.
And the second question is very simple. How about computational effectiveness, for example, in comparison with traditional machine learning methods?
It's slow.
So do you require GPUs, CPUs?
No. I mean, we do this in regular laptops and things like this. But for the typical, I mean, there is this thing. I'm a physicist and I'm not typically very concerned about scalability and things. And I know that, therefore, everything I do in my life is going to be limited to some application and so on. But typically in science, right, if I do experiments in turbulence, I don't have millions of points. I have thousands of points or things like this, right? Well, more and more people have, I don't know, more points, right? But for many, at least, let me put it this way, for many applications in physics, you don't even have thousands of points. You have tens of points, hundreds of points, perhaps. So we can do tens of thousands of points without problem. It takes hours or days to get this on a regular computer without GPUs or anything like this. It's not particularly fast, but again, if I have to find a good model, like people have been using the gravity model or the Nicorazza scaling for 90 years, right? So if it takes me a few weeks or 2 days or 3 days to get a mathematical expression, I'm personally happy with this. Yeah.
Just one question. Maybe you answered on the last slides, but I didn't understand it well, right? So I was surprised when you were showing like this video of evolving those evaluation measures on the synthetic example. Mm-hmm. And it seems that the equation was not very complex. And also the noise, it didn't seem so large, right? But it didn't converge to a single solution at the end. So what is the reason for that?
Well, because there is we are using probability theory, right? So what we are finding, well, I mean, you say the expression is not very complicated and the noise is not very large, but I can tell you that expression with standard symbolic regression approaches, you don't find it. So it's pretty hard actually for most symbolic regression.
Yeah, but you wrote that expression. So what was the expression? What was the correct answer?
The correct answer is something like, I don't remember exactly, but it's x1 times x2 minus a times cosine of x2 plus a or something like that. I don't know. It's a product of two linear functions and a cosine. It's not very complicated, but it's not trivial. Again, if you take Eureka, if you are familiar with this sort of approaches, Eureka, is a symbolic regression package, and you try to find it. It finds the expression, and then it discards it and finds expressions that it thinks it's better. And same thing with all other approaches. So it's not so easy. And the function goes between -1 and 1, and the noise is level 0.1, so it's 10% more or less of the noise to. So it's not that easy. But anyway, we are using probability theory. And what this is telling us is that this expression, the correct expression, is more plausible than the others, that there are still other expressions that could have generated the data, right? A difference in 10 in the description length, 10 bits in the description length, means that the probability of one model versus the other is e to the -10 or e to the 10, right? Mm-hmm. Which is a pretty large number, but it's, I don't know, thousands of times more plausible one model to the other. But if I sample thousands of models, I'm going to find some of those models with probability. So again, it's like in a physical system, right? The ground state might be much more plausible than the other configurations of the system, but the configurations of the system that you see in equilibrium are not the ground state, are other configurations.
So, but probably you get at the end a couple of these equations, and then you try to interpret them using some background knowledge, which one is more,
that's something
plausible.
That's certainly something you can do. If you want to do predictions, you can average over models. For instance, that's the probabilistically optimal method. Let me say another thing too. It's true that you're going to sample other models, but you sample models proportional to their plausibility. So if a model is 10 times more plausible than another, you are going to sample this model 10 times more frequently than this one. So it's because it's Markov chain Monte Carlo, it's not a heuristic. You are sampling proportional to the posterior. So yeah, you can do things. You can get what we did with the mobility. We got the minimum description length model, which is the ground state, the most plausible model, and looked at it. That's one of the models I showed. The other model is the one that resembles the median prediction of the model. So the model that resembles the ensemble of models on average best. Those are the two models I showed. And we didn't, so we got gravity-like models without looking for gravity-like models and things like this.
Okay, thank you.
Thank you. Just a quick question/comment, because you're mentioning extrapolation, that it works better in these models. What? Extrapolation out of range, I guess, of the trained range of parameters. So this is very interesting because, of course, you have some guidance, having a function, how it should go. But I guess one should be very careful of doing that, right? Because you can have new physical phenomena outside of the range. So, I mean, one is tempted, I guess, with these models actually to extrapolate, but there should always be a caution on that, right?
Yes, you're absolutely right. And in this particular example of the turbulence, I don't know enough about turbulence to say, but I think there is nothing else after the range that we are measuring here, that is being measured here, velocities. I don't think there is any new physics beyond this. If you increase in velocities, or at least at velocities that people have been trying experimentally, so things become flat. There is a scaling relationship between the friction and the turbulence. You recover that. But of course, if at some point there is a change in physics and some other phenomena kicks in, or some other, like in your differential equations, another term becomes irrelevant or becomes relevant, of course, you are not going to generalize well. Even then, I would say that the machine scientist in our experience generalizes better than machine learning in general. And I think the reason is because asymptotically, things in nature, the things that we worry about in science, typically, asymptotically, they become linear, or they become quadratic, or they scale with some power, or they grow exponentially, or they become flat. And these are the kind of expressions that the machine scientist is looking for. And that's not by chance. It's because we use these expressions because we've seen them over and over and over as being useful in nature. So in some sense, our prior expectation, or the prior expectations about the world of the machine scientist, are much more aligned with the real world, or the natural world, if you want, than
it depends, I think, on the physics.
The prior expectations of deep learning, for instance, right?
Yes, compared to deep learning, for sure, right?
For instance, if you make a neural network with hyperbolic tangent activations, the prior expectation, if you put random weights in there, everything you generate asymptotically goes to 1 or to constants. Well, the nature is not like this. And we don't realize when we do deep learning that we are putting those assumptions in our models. And well.
Okay, great. Thank you so much.
Thank you.
I think we went seriously over time.
Yeah,
I try to compensate. Thank you so much. Is it yours? Yes.